Dear students, so this is the second problem we are going to solve on damped vibration. So this is the problem statement. The mass of a machine is 100 kilogram. Its vibration is damped by a viscous dashpot which diminishes amplitude of vibration from 40 millimeter to 10 millimeter in 3 complete oscillations. If the machine is mounted on 4 springs, each of stiffness 25 kilonewton per meter, determine the resistance of the dashpot at unit velocity and the periodic time of the damped vibration. Okay, so here a damper is used to reduce the amplitude of vibration. The initial amplitude of vibration has been measured to be 40 mm. After 3 complete oscillations, the amplitude of vibration was noted to be 10 millimeter. So here in the problem, it is asked to find out the resistance of the dashpot at unit velocity and the periodic time of the damped vibration. So the data given in the problem. So the first data is the mass of the vibrating system. M is equal to 100 kilogram. The initial amplitude is 40 mm and xn, that is the amplitude of vibration after 3 complete cycles, x3 is 10 mm. Number of springs provided to the setup are 4. Stiffness of each spring S is equal to 25 kilonewton per meter. So that is 25,000 Newton per meter. Damping velocity is 1 meter per second. That is, it is asked to find out the resistance of the dashpot at the damping velocity of 1 meter per second. Okay. So in the first subdivision, we have to calculate the resistance offered by the dashpot at unit velocity 1 meter per second. And in the second subdivision, it is asked to calculate the periodic time of the damped vibration. That is T suffix P. Okay. So in the first subdivision, it is asked to calculate the resistance of the dashpot, that is damping coefficient. So we can calculate the damping coefficient from the expression of damping ratio. Damping ratio is zeta as the ratio of damping coefficient and critical damping coefficient. So here we are asked to calculate the C, damping coefficient. So there is a formula for Cc, that is 2m omega n. So using this formula we can calculate the value of Cc, and if we know the value of damping ratio theta, then we can calculate the value of C. So Cc is 2m into omega n. Omega n is root s by m. So here totally there are 4 springs are used, each of having stiffness of 25,000 Newton per meter. So the equivalent stiffness of all the 4 springs are 4 into 25,000, that is equal to 1 lakh Newton per meter. 2 into mass is 100 kilogram into equivalent stiffness 1 lakh divided by mass is 100 kg. 6324.5553 Newton second meter inverse. So the damping ratio zeta can be calculated by calculating the logarithmic decrement. Okay. So here in the problem statement there are data to calculate the value of logarithmic decrement del. So logarithmic decrement del can be calculated using the relationship 2 pi zeta root of 1 minus zeta square, and another formula for calculating logarithmic decrement is ln of xn by xn plus 1, and it can be calculated using 1 by n ln of x naught by xn. Okay. So now using this third relationship equation, first we can calculate the logarithmic decrement value. Here there are data for the initial amplitude and the amplitude of the third cycle. So we can use this formula 1 by n ln of x naught by xn as 1 by 3 ln of x naught divided by x3. So x naught value is 40 mm, x3 value is 10 mm. So 1 by 3 ln of 40 divided by 10. So the del value can be calculated as 0.4621. Okay. So now we can use this relationship equation between the del and damping ratio as del is equal to 2 pi zeta divided by root of 1 minus zeta square. Del value has been calculated in the previous step as 0.4621. So here there is only one unknown, that is zeta, which can be calculated easily. So rearranging this, we can have the relationship equation like this: 0.4621 into root of 1 minus zeta square. Okay. On squaring both the sides, 4 pi square zeta square is equal to 0.4621 square, that is 0.2135 into 1 minus zeta square. So this is 0.2135 minus 0.2135 zeta square. On simplifying the above expression, we can have the expression like this: 6919 zeta square is equal to 0.2135, from which we can calculate the value of zeta as 0.0733. So our objective is to calculate the value of damping coefficient C, for which only we have calculated the value of damping ratio and the critical damping coefficient Cc. On substituting the values of damping ratio and the critical damping coefficient, we can calculate the value of C. So zeta value is 0.0733. C divided by Cc value is 6324.5553. So C is 463.5899 Newton second meter inverse. The definition for C is damping force per damping velocity. So in the problem it is asked to find out the resistance of the dashpot, that is damper, per unit velocity. So this is 463.5899 Newton per meter per second for 1 unit velocity, that is 1 meter per second. So next, in the second subdivision, it is asked to find out the time period for one oscillation. So that is Tp. So this has to be calculated for the damped vibrating condition that was asked in the problem. So normally the formula for Tp is 1 by Fn. So here it is asked to find out the time period for one amplitude of damped vibrating condition. So here we have to calculate the 1 by Fd. So we know the relationship between the damped vibrating condition and undamped vibrating condition, from which we can calculate the value of Fd as omega d by 2 pi. So omega d is root of 1 minus zeta square into omega n is root of s by m. Omega n value is root of 1 lakh divided by 100. Omega n value as 31.6228 radian per second. Okay. So by substituting the values of zeta and omega n, we can calculate the value of omega d as 31.5377 radian per second. Now we can calculate the value of fd as omega d by 2 pi. So 31.5377 divided by 2 pi, that is 5.0194 hertz. Okay. So now we can calculate the time period for one amplitude under damped vibrating condition as 1 by ft, that is 5.0194